Okay, so section 4.2 is part of your homework. I may need to add it to the grade book. Um, but the section is on linear approximations and differentials. So we looked at a linear approximation at the end of last class. So when they ask for a linear approximation, they're just asking for the equation of the tangent line. So we take our function and find the derivative. Then we plug in the a value that they gave us to find the derivative at that number. That's the slope of the tangent line. Then we also needed the x and y value, the x1, y1, to find the equation of the tangent line. So we had the x value was -2, but we needed to know the y value. So we plugged -2 into the original function to get that value. And then we just used our normal point slope formula. And I solved it for y because they had L of x equals. You could probably even type -31 times x minus -12, and then just write plus 14 outside the parentheses, and it would take that. Like you don't necessarily have to completely clean up your answer for web work to take it. Like certainly in pre-cal, it could be a lot more particular, but in cal, the answers tend to be, as long as it's equivalent, it's fine. So you can type in messier answers as long as they're technically correct. So linear approximation is just equation of the tangent line. And as long as we're looking at values close to the input we picked at -2, then this line will give us a close approximation of what the function is doing near -2. The further we go from -2, the less accurate the line will be. But if we're plugging in like -2.001, the line is going to be very close to what the function value is. But if I plug in like -1, it's going to be a little or even a lot off. So the other thing that's covered in this section is what's called differentials. So differentials are just a slightly different way of thinking about the derivative. It kind of combines looking at how we were doing implicit differentiation. But what differentials are saying is, so like one of our notations for the derivative is dy over dx, right? And some calculus teachers will be like, that's just the way you write y prime. And like, that's not a fraction. Those are not two separate things. They're lying. Those are two separate things. dy is a separate thing from dx. So when we have dy over dx, we can multiply both sides of an equation by dx and separate the two. And when you get into Cal 3, we do this kind of thing. This is one of the ways we can work on and solve a problem. And there's a lot of engineering applications where this happens. Because in engineering, you'll have a system where you've got X and Y coordinates, and then you're having to do something else with it, which means it's a third variable. Multivariable calculus, interesting things can happen. So all it really is, though, is a notational shift. So whenever we take, like if we have, let's say, y equals x squared plus 2x plus 7. If I'm going to take the derivative, like normal dy dx, then that would be 2x plus 2. I can then multiply by dx, and I have my differential equation dy equals the quantity 2x plus 2 times dx. I could distribute the dx through. I could leave it like this. If this was the question and they asked for dy, this is what we would type as the answer, 2x plus 2 with a dx. So we can either distribute the dx through or leave the parentheses. But another way to think about it, same function, is when I'm applying the derivative, I just apply it to both sides of the function as a thing I'm doing. So dy, derivative of y is dy. Then derivative of each of these things, derivative splits across addition. So I have derivative of x squared plus derivative of 2x plus derivative of 7. Now we're going to use the chain rule. So derivative of x squared, thing squared, we bring the power down 2 times thing to the first. So 2 times x to the first times derivative of thing, derivative of x, we say dx now. Plus, now the derivative of 2x. Well, the derivative of 2x is just 2 times the derivative of x is now dx. Plus the derivative of a constant is just 0. And even if we wrote 0 dx, 0 times something is still 0. So we end up with the same derivative, just a slightly different way of thinking through the process. Both ways totally work, especially when we start with an equation where the y is completely separated from all the x terms. We can just do our derivative like normal and just multiply by dx. But eventually you'll have problems where the x's and the y's kind of get mixed together. And being able to think about it from this, well, I can just take the derivative and I use the chain rule everywhere. Like even with the derivative of y, I should have said like 1 times dy. Because derivative of a thing is 1 times the derivative of y. All right, so this question from the homework, they gave us that. So that is a disgusting quotient rule, or we could turn it into a product chain rule. In either case, it is very gross. But since the bottom is a square root, at least in the quotient rule, we'll have the bottom squared, so the square root will cancel, so that'll be okay. So I'll go with the quotient rule here, but it's ugly. Now, first change I'm going to make, not doing a derivative, I'm just changing out the square root for the 1/2 power. All right, now I'm going to use the quotient rule. So if I call this high and this low, low d high minus high d low, square the denominator, and away we go. So our dy dx is low x plus 8 to the 1/2 times d high 5 times 2x, and then the derivative of the minus 5, that's just a constant, so that's 0, so I'll close my parentheses there. Minus high, keep the 5x squared minus 5, and then the derivative of the bottom, a little bit uglier, but that is a thing to the 1/2 power, so I'm going to use my power rule. 1/2, keep thing the same to the -1/2, and then times the derivative of the inside. The derivative of x plus 8 is 1 plus 0. And then all over the square root of x plus 8 squared. So that whole crazy mess is what we're going to type in the first blank. I'm not going to try to clean that bullshit up. It's fine just like that. Well, fine is maybe not there is no reason to go through the effort of trying to clean this up. Just make sure you've got parentheses in all the correct spots. I mean, if you don't want to type the times 1 plus 0, like, sure, we can make that part go away. Now, the second question here is saying, evaluate the, well, okay, sorry. I forgot one step. We had dy dx. We need it to be just dy by itself. So I got to multiply by dx. So after I type that whole ridiculous fraction, at the very end, I should have times dx outside the fraction. Now, the second half where they say evaluate the differential of y at x sub 0 equals 2 and dx equals 0.6. So they're saying everywhere we have an x, put in a 2, and where we have dx, put in 0.6. So it's 2 plus 8 to the 1/2 times 5 times 2 times 2 minus 5 times 2 squared minus 5 times 1/2 times 2 plus 8 to the -1/2 all over the square root of 2 plus 8 squared times 0.6. Now it is quite possible we could just type that thing with the numbers in and WebWork would take that. But it's not bad practice to type that entire craziness into the calculator, but God, is it awful. So I'm going to do this in stages. I'm going to type everything that's on the top of the fraction and then hit enter. All right, so my top is 60.87, blah, 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 blah. Now I'm just going to type divided by and then times 0.6. It said enter your answer accurate to 4 decimal places, if not an integer. So 3.652430. Yep, it took that for the second answer. I am not wasting the time on typing in that top bullshit. So questions on what these are asking when they ask for the differential of y are ways to kind of think through that. All right. Then what we're looking at now is the mean value theorem. So we're going to think back to some of our older terms, average rate of change. So what is average rate of change? A really long way of saying. What's that mean? Yep, slope. So they want to know what's the slope between 3 and 7. Well, I need to know the ordered pairs. So at 3, my y value is 4. And then at 7, my y value is 8. The slope is change in y's over change in x's. And we end up with 4 over 4, which is 1. So I know it doesn't totally look like a slope of 1, but if you look at a little more closely on the graph, you'll notice that those aren't squares, those are rectangular boxes. So that's why it looks like a slope of less than 1, but our calculation is 1. Like when I sketched it in, it is going from diagonal corner to diagonal corner on all the boxes, all the rectangles. If we made those rectangles square, it would look like a 45-degree line. All right, so we got the slope was 1. And now they want the equation of the tangent line. So we had the point 3 comma 4. So y minus y1 equals m times x minus x1. So we get x minus 3 plus 4 is y equals x plus 1. So that's just the equation through those 2 points. A secant line, secant in this instance is just saying it's a line that goes through 2 points on the curve, as opposed to a tangent line, that only touches the curve at one point, presumably. All right, now it asks, well, how do we find the equation of the tangent line of this function at 3? So to get the equation of the tangent line, well, we'd have to know the function to calculate the derivative. But just looking at that point, so we'd figure out the derivative and plug in 3. This would be the slope. And then we would use the slope and the point to find the equation. So we'd have to find the derivative. Is this line going to be the same as our secant line? No, they are vastly different. So this is just a review of how, like, a secant line works versus our tangent line. The tangent line is the instantaneous rate of change, or the slope at a point. So even though technically that tangent line does actually hit the graph at another point, close to the point in question, it's only touching the curve at that one point. So even though it coincidentally hits it again down here, it's still tangent at that point. So what the mean value theorem is asking is there anywhere on the graph where the slope of the tangent line looks like it would be equal to the slope of the secant line? So if I take parallel lines to my secant line, like, are there places where I could stop my parallel line and I'm going to cross the curve in one point in a tangent way? So if I just start sketching parallel lines, I can see there's a point down here. And I can also see there's going to be a point over here. I couldn't make sense of the Desmos activity Christy had made, so I'm not doing that. So there's two places on this graph where the slope of the tangent line is going to be the same as the slope of the secant line. So what the mean value theorem says is, as long as f is continuous over an interval and it's differentiable on that interval except at the endpoints, then there's at least one point in the interval whose derivative is the same as the derivative between the slope between the endpoints. So when we look back at the picture, the mean value theorem was guaranteeing this point existed, because that point is between our A and our B value. So in between those two, we had a slope of 1. Somewhere else between 3 and 7, there had to be another point that had a tangent slope, a derivative equal to 1. Now, there happened to be a secondary point. The mean value theorem doesn't guarantee that secondary point, because if this was a parabola, if the graph just kept going like up, then there'd only be that one point. So the only one we get guaranteed from the mean value theorem is somewhere in between the 2 points. There has to be a point that has that slope. So now we're going to have weird questions. Well, they say find the value or values of C in the conclusion of the mean value theorem for the given function over the given interval. So that's our conclusion of the mean value theorem. So the right side of the equation, f of b and f of a over b minus a. My 0 and my 8, those are my a and my b. So to figure out what I'm going to set the derivative equal to, I'm going to calculate the slope from x equals 0 to x equals 8. So I need to figure out what f of 0 and f of 8 are. So f of 0 is nice and straightforward. I mean, f of 8 is as well. We just got to use the calculator. So 8 times 8 to the third minus 2 times 8 minus 20. 4,060. So we're going to do f of 8 minus f of 0 over 8 minus 0. So 4,060 minus negative 20 all over 8. And this actually equals just one nice number, relatively nice, 510. So that is the slope we're looking for. So now to solve, now we're going to take the derivative. So I have y equals, so now y prime equals 8 times the derivative of x cubed. Power rule, we bring the power down, so 3x squared. Minus 2 times the derivative of x is 1. Minus the derivative of a constant is 0. So I have 24x squared minus 2. I want to figure out what x values or c values, if I want to write it in terms of c, whatever. When does this derivative equal 510? So I'm going to set it equal to 510. And now we're going to solve this equation. So we add the 2 over. Get 512. Now we're going to divide by 24. Oops. All right, both of those are divisible by 8, so we get 64 thirds. Sorry, x squared equals 64 thirds. And to get x by itself, we're going to square root. Whenever we square root, we have to remember the plus or minus. So on top, the square root of 64 is 8. The bottom can just stay the square root of 3. So we've got plus or minus 8 square roots, 8 over the square root of 3. So those are the two places where the slope is 510. Those X numbers. Now the negative number is not going to be between 0 and 8. The positive number will be 8. Square root of 3 is bigger than 1. So 8 divided by the square root of 3 this is plus or minus 4.618802, blah, blah, blah. So it's between 0 and 8, but our answer is only going to be the positive one. So from x equals 0 to x equals 8, the slope is 510, ridiculously nearly vertical line. And at a little past 4.5, that's the x value that the slope of the tangent line is the same as 510. So what questions do y'all have on how this problem shook out? What it asked us to do, how we did it? All right, well now we got a weirder interval because the function, well, the interval is nice, 0 and 1, but the function is a trig function. It's actually a chain rule setup. But still, we're going to start it out the same way. We got to figure out f of b and f of a. So f of 1 is sine times pi times 1. So that's the sine of pi. So when I'm trying to remember like what the trig functions do, I think about their graphs. So sine starts at 0. At pi over 2, it's up at 1. At pi, it's back to 0 again. So the sine of pi is 0. Then when we substitute 0, we get the sine of 0, which is also 0. So f of b is 0 minus f of a is 0, divided by b was 1 minus 0. So we're looking for between the values 0 and 1, where is a value that has a tangent slope, a derivative equal to 0? So since my two endpoints have the same y value, the secant line between those 2 points is a flat line. So somewhere in between these 2 points is another point that has a flat line derivative. So this is the conclusion of the mean value theorem. Like, this is what we use the mean value theorem to do a lot of the times, is if I can intersect the graph with a flat line, then between any 2 points that flat line intersects the graph, there's some value in between where the tangent line is also flat. Now, a sine graph, like almost anywhere I draw a horizontal line, it's going to intersect the graph over and over and over again. But there's a lot of places, because the sine graph repeats values over and over again, so there should be a lot of x values where there's a flat line. All right, so now we're going to have to do our derivative. So we have the derivative, we have sine of thing. So the derivative of sine is cosine of thing times the derivative of thing. The derivative of pi times x, that's just a number times x, so it's pi times the derivative of x is 1. So when I have cosine of pi x times the pi times 1, that is not being multiplied inside the cosine function. That's being multiplied outside the cosine function. So I have pi times the cosine of pi x. And this is what I'm going to set equal to 0. So now I'm going to divide by that pi that was on the outside. So I have cosine of pi x equals 0. So now I want to think about my graph of cosine. So cosine starts at 1, goes to 0, down to -1, back to 0, and back to 1. So the x values where cosine equals 0 is at pi over 2 and 3 pi over 2. So when I'm solving this trig equation, I've got the inside pi x equals those two angles that I just figured out from the sine graph. I could also pull them from the unit circle. So cosine is 0 at pi over 2 and at 3 pi over 2. Now, when we are solving trig equations, when we pull numbers from the unit circle, this is where we also put plus 2 pi k. Now, it's probably not going to matter on this question if we forget the 2 pi k part, but I just habitually, when I'm at the point where I write angles down, I always put my 2 pi k there. So that way, on the off chance I did need it, I put it down at the correct time. Now, my inside of my trig function was not just x, it was pi x. So now I have to get rid of the pi. So we are going to divide by pi. So pi over 2 divided by pi leaves us with 1 over 2, plus 2 pi k divided by pi just leaves us with 2k. And then we also get 3 halves plus 2k. Now our interval was from 0 to 1. So looking at my equations, 1/2 is between 0 and 1. If I plug in a k value of 0, I get 1/2. If I plug in a k value of 1, I'm going to get something bigger than 1. If I plug in a k value of -1, I'm going to get something smaller than 0. So k equals 0 gives me an x value of 1/2. That's between 0 and 1. If I plug in k equals 0 over here, I get 3/2. That's too big. If I plug in -1, 1/2 minus 2 is -3/2. Too small. Same thing over here. 3/2 minus 2 will be -1/2. Too small. If I plug in +1, 1/2 plus 2 is 5/2. Too big. Three halves plus 2 is 7/2. Too big. So the only solution we get is x equals 1/2. All of these others are solutions. They are other x values where the slope of the tangent line is 0. But x equals 1/2 is the only number between 0 and 1. Now you don't have to write through testing all of the k values for that. I was just writing it down so it was like a visual representation of the words I was going through. But overall, same thing, just it was a little bit hairier because it was a trig equation we were solving. All right, now our last example is a natural log. And our interval is from -1/2 to 7/2. Okay. So first things first, we're going to do our f of b and f of a. So this gives us the natural log of 4 times 7/2 plus 6. So this gives us the natural log of 20. Then f of a is f of -1/2. So the natural log of 4 times -1/2 plus 6. So that's -2 plus 6 is 4. So the natural log of 4. So we get the natural log of 20 minus the natural log of 4 all over 7/2 minus -1/2. So that'll become plus +1/2. So 7/2 plus 1/2 is 8/2, which is 4. So the natural log of 20 minus the natural log of 4 all over just the number 4. This is what f prime of c, our derivative, is supposed to be equal to. So now we need to find the derivative. So the derivative of natural log of something. So the derivative of natural log of u is 1 over u times du dx. So our natural log of 4x plus 6 will be 1 over 4x plus 6 times the derivative of 4x plus 6, which is 4 times 1 plus 0. So that's just a times 4. So we have 4 over 4x plus 6. Now, some people get overexcited seeing those two 4s and decide to try to cancel them. Do those 4s cancel? Why not? Yep. In order to cancel, my outermost operation has to be multiplication and division. My outermost operation on the bottom is addition. So if I factored a 4 out of the bottom, then I could cancel, but then my bottom would look a little clunky. So it's not that we can't cancel the 4, it's just that we have to be careful in how we do it. So there's my derivative. I'm going to set this equal to that horrible mess over there. All right, so we have a fraction equal to a fraction. So I'm going to multiply both sides by 4. And I'm going to multiply both sides by 4x plus 6. So on the left side, the 4x plus 6 is cancel, and I'm left with 4 times 4 is 16. On the right side, the 4 on the bottom cancels with the singular 4 I multiplied by. So I'm left with natural log of 20 minus natural log of 4. That thing times 4x plus 6. Now I say that thing times 4x plus 6 because that thing is a number. I don't want to FOIL that out when one of the pieces is just a number. I don't need to multiply this out. I'm just going to divide by the horrible looking number part. So it's going to look weird. But now on the right side, it's just 4x plus 6. And the left side is this weird, stupid looking fraction. So now I would minus 6 on both sides. And then I would divide by 4, but over on the other side, I'm going to write that as multiplying by 1/4. So there is our x value. Now we do need to know if this x value is between negative 0.5 and 3.5. Now, since it's web work, like we'd get a question like this on web work, we could just type in that number and see if web work takes it. And if it does, cool, we're done. And with the way the mean value theorem works, since the function is defined from negative 1/2 to 7/2, like this has to work. So I'm really just typing it in just to show that like it does work. So I'm just going to do the little fraction first. So 16 divided by the natural log of 20. But when I go to type this, my calculator, when I type natural log, opens a little set of parentheses. So I'm going to write those parentheses in so I can like follow, am I putting my close parentheses in the right spot? But I'm also going to need parentheses around the bottom. So there's a lot of parentheses just to type that little fraction. All right, now I'm going to minus 6, hit equal, and then divide that by 4. So it is bigger than negative 1/2. It is smaller than 3.5. So that is our x value where the slope is that stupid fraction. So the homework on this particular section is going to give you more practice doing derivatives. Based on the few tests I've graded so far, y'all need more practice doing derivatives. Like that's the downside of the web work homework is like each question is a singular example, but for each one of those, you should really be doing several of them. So as like mean as it is to say, you should do more homework. When you're learning how to do derivatives, you need to learn it by practicing, which means you need to go do more and more derivatives to where you know without thinking about it, oh yeah, derivative of natural log is 1 over thing times the derivative of thing. So that way when you're applying like the chain rule here, you can apply the chain rule without having to think too hard about it. You can very quickly recognize, oh, this is a product, this is a quotient rule, and use those rules quickly. That speed, that comfort comes from practice. So mean value theorem questions. We calculate the average rate of change by finding the y values, the difference of those over the difference of the x values. We take the derivative, we set the things equal to each other and solve.
On that last part, how did you get rid of the 4x plus 6 on the right? When you were multiplying?
So you mean in here?
Yes, like you multiply. Is it multiplied by the top and bottom or just?
No. So that is, we were multiplying both sides of the equation by 4x plus 6. So on the left side, it canceled the 4x plus 6 on the bottom. On the right side, it's just 4x plus 6 over 1. So that's why it's here. I've got that natural log of 20 minus natural log of 4 that was still on top. And then it's times the 4x plus 6 just next to it in parentheses. All right, so the homework for mean value theorem is just 4 problems. And the 3 examples we did are basically problems 2, 3, and 4, more or less. Problem 1 has an applet on it. So we've got a graph, and we've got a secant line drawn between 2 points. And they give us the formula for the secant line here. Negative 0.85x plus 0.92. And then there is a point here. And when I drag it around, that is calculating the equation of the tangent line at that particular point. So underneath the graph, they're saying the function depicted is clearly continuous on the interval and differentiable on the interval. So that is what we need at the start of the mean value theorem. Drag the point colored blue to change the tangent line and find the approximate value of C that satisfies the conclusion of the mean value theorem. So they want us to move the tangent line until we have an equation of a tangent line that has the same slope. So I go between A and B. So the slope at A is 0. The slope at B is like negative 1.63. So somewhere in between there, it should hit negative 0.85. So I'm just carefully moving my X value, my point. And then I'm going to zoom in. And that appears to be at negative 1.7. And I hit check, and Weber likes that. Now, I will point out here on problem 2, there is a negative sign in front of this whole polynomial. That negative sign is very easy to miss. Yours may not have a negative, I don't know, but just mine that rendered here does. All right, so those of y'all that have been working on stuff, are there any questions you want me to go back through? Oh yeah, this guy. All right, let me grab a picture of this. Yoink it over to OneNote. All right. So they're saying if I can write something as, I'm going to rewrite this a little. 1 plus ugly to the k. Then this is approximately the same as 1 plus k times ugly. So it doesn't have to be just an x. It can be a little bit weirder, but we do want it to be 1 plus the thing and then to some number power. Now this does say for x near 0, but the approximation we're looking at is kind of similar to some of the crap from the end of Cal 2. So what I want to do with my functions here is I want to rewrite them so they look like 1 plus a thing to the k power. Now they might be multiplied by something on the outside. There might be something added to them on the outside, but I'm trying to get the internal part to be 1 plus some x thing to the k power. So when I look at this first function, the negative of 5 over 1 plus 2x, I'm going to rewrite that as negative 5 times 1 plus 2x to the negative 1 power. Now that's not what we're typing in for our answer. That's just what the function is equivalent to. Now our 1 plus 2x to the negative 1, that's 1 plus ugly to the k. I'm going to trade that out using my formula here. So the 1 plus 2x to the negative 1, they're telling me I can trade it out for 1 plus negative 1 times 2x. And then the negative 5 that we had in front just carries through. So when we make that trade, we're saying our function is similar to this line. So this is negative 5 times 1 minus 2x. So if I type that in, that's what they want for the first answer. All right, my second answer, I'm going to try to do the same thing. I'm going to try to make it look like 1 plus a thing to a power. So let me write that function down first. All right, so I'm going to trade out my square root for the 1/2 power. But my inside here, the 2 minus 8x, I need to factor out a 2 because I need it to be 1 plus a thing. So it's going to look a little weird. So when I pull 2 out of 2 minus 8x, because I'm still leaving my 1/2 power outside all this. So that'll leave me 1 minus 4x. So 2 times 1 is 2. 2 times minus 4x is minus 8x. So this is equivalent to what's inside the square root. Now 2 times a thing, all of that being square rooted, I can split the square root across multiplication. So my function can be written as 2 to the 1/2 times 1 minus 4x to the 1/2. Now I'm going to rebrand my 1 minus 4x though as 1 plus negative 4x. Now it's matching my 1 plus u to the k. My u is negative 4x, my k is 1/2. So I'm still going to have this weird 2 to the 1/2, which I could type as the square root of 2. But my 1 plus negative 4x to the 1/2, I'm going to trade out for 1 plus 1/2 times negative 4x. That's what f of x is approximately equal to. And I could clean up the 1/2 times negative 4, like this is 1 minus 2x, still with the square root of 2 on the outside. But WebWork will take either answer. You don't have to clean up the answers. And then we get the last part, and the last part is asking us to work with a really stupid looking formula. So in Einstein's corrected formula, mass has the value m equals blah, where big M represents the mass of an object at rest, v represents the velocity of the object, and c is the speed of light. If we assume that v is small compared with c, then we can find an approximation to the mass of the object to be. So the whole wrong button. So the whole v is small compared with c is just saying, like, we can use the approximation formula. All right, so let's write that stupid formula down. Little m equals big M divided by the weird square root of 1 minus v squared over c squared. C is a constant, and m here is another constant. So v is our variable that we're focusing on. So first thing I'm going to do is rewrite this formula. So little m equals big M times 1 minus v squared over c squared to the negative 1/2 power. All All right, so remember our approximation formula is 1 plus u to the k is 1 plus ku. I have 1 minus thing to the k. So I'm just going to rewrite this as plus negative. So I can trade out this part for 1 plus negative 1/2 times negative v squared over c squared with the big M in front. And that's what they want for the third answer. So big M, parentheses, 1 plus v squared over 2c squared. So this is just a weird application of linearization. Not something we're going to ask on the test, especially not that weird interpret this esoteric formula. But applying the rule, the 1 plus u to the k equals 1 plus ku, like that's still good math to be familiar with. Because we do a very similar thing towards the end of Cal 2 with all of the weird series that we look at. But excellent question, because that was the weird question in 4.2. So y'all's numbers might be a little different. It may not be -5, maybe it'll be -3, and maybe instead of 2x, it's 4x. I don't know, but the overall idea we did is going to hold true.